Yeah, hello everyone. Welcome in this last session of this workshop. So second last session of this. So topic of this talk is unleashing the power of quantum from foundation to next generation communication systems. And speaker is Dr. Sudip Biswas. So let me introduce him briefly. Okay. So, Dr. Sudip Biswas is an associate professor in the Department of Electronics and Communication Engineering at the Indian Institute of Information Technology, Guwahati. Uh, Dr. Biswas received his PhD in digital communication from the University of Edinburgh, UK in 2017. And previously, he worked as a research associate in the same department, University of Edinburgh. And focused on optimization, signal processing for 5G and beyond communication systems. So he also brings valuable industry experience from Tata Consultancy Services India. He currently serves as an editor for IEEE Transaction on Green Communication and Networking, and has held key organization and technical roles across major IEEE conferences, including IEEE Globecom and ICC. Professor Biswas has been actively involved in multiple EU, European Union, UK, and Indian government-funded research projects, and is currently leading several SERV and DST Indo-Taiwan and ISPARC projects. In today's session, he will discuss foundations and quantum-enabled networking for 6G, Open RAN, focusing on optimization and secure decision making and edge intelligence. So please let's welcome Dr. Sudip Biswas.
Thank you so much, Keshav, for the wonderful introduction. Actually, so for some of you who might not know, Keshav and I go a long way back. Actually, so I was doing my PhD in the University of Edinburgh, and Keshav was a postdoc back then. So we just happened. So I'll just give you another, just a slide, means how we introduced each other is that. So when I means what happens is that when you see someone, some Indian in a foreign country, what you usually do, you usually try to speak in your mother tongue. You speak in your mother language. So I spoke to Keshav in Hindi, and he responded in English. So I thought, this is a very arrogant person. I don't want to talk to this person anymore. So after that, for around 2-3 months, I never spoke to him. It's okay. But somehow, as fate had it, so we gradually got to know each other, and since then we have become very close friends. And so I know his family, I know his wife, I know his children, and we are very close friends. And so we have also worked on a lot of joint projects and joint work. And again, so the idea of quantum actually means, so me and Keshav, we were working on radar LTE coexistence back then. We have a mic or something that I can roam around. Oh, yeah, okay, that's great. So we used to work a lot on radar LTE coexistence. Many of you today, after almost 7, 8, 9 years, know it as ISAC, Integrated Sensing and Communication. But we were one of the earlier people who were working on spectrum sharing and radar LTE coexistence. And one of our papers, it was very well appreciated by the research community as well. Back then, the term ISAC was not there, but one issue that we used to face, we used to have very high computing, highly capable computing computers in Edinburgh. But one issue that we used to have is that computing. So it is to take a lot of time, those combinatorial problems that we face in those complex optimizations that we need to solve in multiple dimensions. So that was always a constraint, computing. How do we make it efficient? And one of the earlier
I still remember we fought with one of the editors or area editors of TCOM or TWC. I don't remember. I think TCOM or TWC it was. And basically, with the computation regarding the computational complexity, he had a lot of queries and he just rejected, and we were very angry. And anyway, so computation was always a concern. The time it takes. So an algorithm. Forget about heuristic search. I mean, it was not possible. It was not possible in 2000. Means the amount of problem, because massive MIMO was a very big thing back then in 2016, 15. So it was just coming up. So reviewers were asking us to consider 1,000 antennas, and with the increase in number of antennas, what used to happen is that the complexity, the time, not only the complexity in terms of flops, but complexity in terms of the time complexity also kept on increasing. So since then, we have been working out various ways, various algorithms, efficient algorithms to make the computation as fast as possible. So recently, a year or two ago, means I was talking to Keshav, and he introduced me to one of his friends called Shahid Mumtaz. He's from NTU, means Nottingham Trent University. He introduced me to him, and we basically got a joint project, India-UK project, and through that we started exploring quantum. And with an application in Open RAN, and Open RAN, as you know, is the next one of the next technologies that's going to empower 6G networking. And so that's how we came across quantum. It's been like 1 years that we are working on quantum, and since then we have published a few papers on that as well. I'm going to go through. I know, means I think I've been given around 1 hour 15 minutes of time, so that's. If you don't get scared, I have around 120 slides, but I'm sure I'm not going to be able to cover all of those, but I'm just going to try to give you brief ideas about quantum computing, quantum communications, and I would also like to talk about some of the applications in Open RAN that we have been publishing of late. So let me begin by asking you a simple question. Okay, so take a classical bit, and if I pass it twice through a NOT gate, what do I get? We get the same thing, right? So now let me ask you the real question. So is there a way to not get the same thing? So is there a way that we do not get the same thing once we pass it through the same gate? Take a classical bit, we pass it through the same gate twice and not get the same thing. So the idea of quantum basically comes from this. So basically the question is that, can computation exist between 0 and 1? Okay, so this is something we're going to explore in today's talk. So this is some of the overview. I don't know how much I'll be able to cover, but means I'll try to touch upon some of the quantum computing stuffs. Means I'm very glad that Professor Octavia has already covered the basics yesterday, so I'll just breeze past those. Then we're going to talk about some of the key applications. Then I'll touch upon quantum computing in Open RAN, and I'll also talk about some of the future prospects that we have with quantum computing and quantum communications. So, how many of you have seen this picture? I can see one hand, 2 hands, 3 hands. Okay, so Aditya, oh, I can see the 4th hand. Yeah. So when we talk about quantum computers, we usually see this picture, right? We see this picture when we talk about quantum computers. So anyone, can you tell me what this is? Is it a quantum computer? It's actually not a quantum computer. The quantum computer here is a very tiny chip. It's a very tiny chip. This is mostly all the refrigeration that happens to keep the quantum computer to sub-zero level. We have to keep it around minus 270 degrees Celsius, so that that small quantum chip can work. And so this is basically known as the golden chandelier in quantum. The main role of this is basically a refrigeration unit that keeps the quantum computer chip to operate, and basically how quantum mechanics we are going to apply it to that chip. So I'm not a quantum mechanics or a quantum physicist by any means. So I'm just trying to apply some of it in my application, that is communication. But in short, means what quantum mechanics does is that it's a branch of physics, means that basically deals with how matter and energy, they behave at the smallest scale. Okay. So when we talk about atomic and subatomic particles, what happens when they interact with each other, that's what quantum world is all about. So you might ask that why do we need quantum now that we have a lot of processing power with so much GPU processing capabilities? Well, the simple answer is that every day the combinatorial nature of the problems, they keep on increasing. Okay, so quantum computing has this spatial, we'll soon see what qubits. Where did it go? It's not working. No, I'm using, it's not. Slides are moving, but it's okay. It's okay. It's not working now. Okay. So what's basically there's something called the qubits, right? There's something called qubits that Professor Octavia mentioned yesterday, and we're going to also look today into more about qubits. And these qubits are something like superpowers that gives processing and that gives computation in another dimension that we are going to soon see. So a brief history about quantum computing, and it's not new, by the way. It's not new. So it was introduced by Einstein as early as 1905. The concept of quantum theory, then physicists Richard Feynman and David Boyce, they proposed the idea of quantum computing. Then, as you saw yesterday, the Shor algorithms and all, they were developed around 1994. Then around 2000, early quantum computers started to come to us. So now let's talk briefly about what those quantum bits are. Okay. So I think many of you already know by now from yesterday's talk that so in classical we have zeros and ones, right? There is absolute zero and absolute one, and quantum basically has something called qubits or the quantum bits, and the superpower is that those qubits, they can be in multiple states simultaneously. Okay. And they can either be zero or it can either be one, or it can be in between in an intermediate state. So, and that superpower comes from two phenomena. One is known as superposition and one is known as entanglement. So many of you might have seen all those sci-fi movies, right? So what they show that suddenly you are teleported from one place to a different place, right? So of course in practice it's not going to happen, but we're going to see that that's means that not entirely false as well. Okay, so that's the power of quantum. Of course it doesn't happen that you will not be ported from Taiwan to the US. It's not going to happen, but information can be ported. So we're going to see that. So there are two phenomena, right? One is superposition and other one is entanglement. Okay, so superposition basically states that a qubit basically exists as a linear combination of two probabilities. One is the alpha and beta, and the squared magnitude of both of them should be equal to 1. And this symbol you already know, I guess, it's known as the ket 0 and the ket 1. That means that until you measure a quantum bit, it can be anywhere between 0 and 1. So this superposition basically enables we're soon going to see how photons also hit light and how parallel exploration of multiple path happens. And the other one is the idea of entanglement. So this is very important because the quantum communication part deals a lot with entanglement. So entanglement basically means that there's a strong correlation between two qubits. If two qubits are entangled, that means that there's a very strong correlation between them. Changing one of them or measuring one of them instantaneously will give you the value of the other one. Okay, so as it says, measuring one of the qubit instantaneously affects the joint quantum state of the other bit. So this basically is a fundamental concept for QKD and all those things with respect to quantum key distribution, for quantum security and all those things in quantum communication. So let's look into a real world analogy. Okay, so as I said, there are two phenomena, right? One is the superposition and one is the entanglement. So let's take an example of tossing a coin. So when you toss a coin, let's say it's a fair coin. Fair coin means the probability of getting a head or a tail is 50-50. So it's not rigged or anything. So until you measure the coin, okay, means until the coin drops or you catch the coin, so there's an equal probability of getting a head or a tail. Okay, so when it's in the air, so we can put an analogy to it that it's in a position of superposition. So it could be either ket 0 or ket 1 until measurement happens for the case of qubit. And for the case of the coin, it could be either head or either tail until you measure it. So that's a real world analogy with respect to superposition. Similarly, for entanglement, what could happen is that, for example, I've given an analogy of parent-child. It could be, for example, some of you means you are sitting here, right? Or I'm giving a talk over here. So let's say my parent in India, my father or my mother in India somehow has gotten sick, let's say, and I have that information. So I won't be able to deliver this lecture with the same way as I'm doing it now, right now. So there's some correlation that has existed before with respect to the relation between me and my father, or with me and my mother, and something happening over there is directly affecting my performance over here, though no direct exchange is happening, right? So that's the analogy I could think of over here. So some shared prior relationship is there, and it's not about some instant communication. It's about some prior correlation, some very strong correlation. And similarly, what happens in the quantum states as well, or quantum systems as well, this entangled particle, they share a joint state, and when you measure them, then you get some correlated outcomes. Again, this is the fundamental behind quantum security or quantum communication. So if means yesterday, Professor Octavia gave an example of your Eve and Bob trying to communicate, and Willie trying to eavesdrop. So as soon as, because the Bob and Eve, they're correlated, they're entangled, so their qubits are entangled. So if Willie tries to eavesdrop that information, or if as soon as Willie measures that information, that the Eve, or for that matter, Bob is going to instantly know about that. So that's how you secure your system using QKD. Okay. So what can quantum computing solve? There are a lot of applications. So anywhere where you have optimization, you can apply quantum computing, be it AI machine learning, because quantum annealing is quite a big thing that's coming up right now. So all those the algorithms that we apply, like VQC and all, they are all part of that. And 5G networks, 6G networks, healthcare, everywhere we can explore quantum. Okay. So now let's go a bit into the depth about how photons work. Okay. So how you actually transmit information using quantum behavior. So till now I was talking about quantum computing. Now so this next couple of slides I'm going to talk about quantum communication. So as you know that light is an electromagnetic wave, right? It's composed of some discrete energy packets which are known as photons. Okay. And each photon basically carries some energy and is given by equal to h times f. F is the frequency and h is the Planck's constant. And so what happens when a single photon encounters a beam splitter? Okay. So as soon as it encounters a prism or a beam splitter, the photon basically disperses. So it takes several different directions. So we will call that the photon is existing in a superposition of paths. So until you measure that photon. So when I said that there is ket 0 and ket 1, so understand that this superposition state will exist until you measure them. So until you measure them, so at the end of the day, when you measure the qubits, it's going to give you some classical information itself. But until you measure them, it's going to be in quantum state or superposition state. So this photon, it exists in a superposition of parts until it is detected or until it is measured. And when this photon hits the detector, so what you're going to do is that you're going to come up with an outcome. And basically the photon will collapse and the superposition state will break. Okay. So this is about so you can also do this for repeated photons. We can also do this for a repeated photon. And if you do this for a repeated number of photons, then what you get is that a wave-like behavior. So once you get this wave-like behavior from these particle-like events, then what you can do is that you can encode some information in the qubits in terms of polarization, in terms of phase, or in terms of path. Okay, because we're soon going to see that the qubits, they exist in a complex space. Okay, we put them in a block sphere, but they're complex. So we can then use these photonic qubits to encode information in either polarization, in either phase, or the path. Okay. So this kind of optical platforms, they will enable quantum computing, quantum sensing, and as well as with the help of QKD, you can also go for quantum security. So looking a bit further, what we understand is that I think this is quite understandable right now. This might not be quite understandable right now, but it will soon be, because we're going to look at how this direction changes to the left or right, and how we can also measure these photons. But in terms of connection to quantum communication, what we can do is that we can take the information and encode it in polarization or rotation of photons. We're soon going to see that. And this is basically the principle that is used in quantum key distribution and quantum links. Any question until now? If not, I'll continue. Okay, so quantum bits. Yeah, so as you know, this quantum bits, it can be both 0 and 1 at the same time. And we have already seen that this is known as the phenomenon of superposition. And it's basically represented something with this notation. It's called the Ketsai. So Kets, this notation Ket. How many of you are familiar with this notation? Yeah, you will be. You are. You have done quantum, but so there is the bra and there is the Ket. So there's the. So have you heard about that? Anyone? Of course you will. So we'll soon see what that is. But in simple terms, basically, what it means that if you take the inner product, if you take a simple bracket means that if you take the inner product of psi in a bracket, then it should give you a unity. Okay, so here the Ketsai basically is a probabilistic weightage. It's a probabilistic weightage of some basic states. Okay, so this alpha and beta, their probabilities and their weights, and basically this probabilities defines whether it is closer to the 0 or whether it is closer to the 1. Okay, so again, as I said in one of the earlier experiments, so if you flip a coin, it could be the heads or tails until you observe it. So that's how a qubit works. So this is known as the Bloch sphere. This is known as the Bloch sphere, and Bloch sphere is nothing but a geometric representation of qubits. Okay, and remember that a general qubit, it can be represented using this equation, where it has two parameters, theta and phi. And also note that it is complex, but we are representing it, we are visualizing it in 3 dimensions. Okay, so this Bloch sphere basically helps to visualize this qubit in qubit states in this point, at some point in this surface, and this theta and phi, they are basically angles which gives the latitude and the longitude in this Bloch sphere. Okay, so this is just to make things easier for visualization. And all the things that happen to qubits, they happen either in X rotation or in Y rotation or in Z rotation, right? So what happens is that we're soon going to see that the gates, the Pauli X, Pauli Y, Pauli Z, and they all does some kind of rotation in this. Either they just rotate the amplitude of the bits, or they just change the phase, or they change both the bits and the as well as the phase. They're going to, each one of them does a certain thing, and it all happens in this Bloch sphere. So this, you have already seen it yesterday as well. So unitary operations, so whatever quantum computing that we apply today in our work. Okay, so before we go into this, let me also introduce you to the state of quantum that we are in. Professor Octavia already mentioned yesterday that we are in the NSYSU era, right? So it's a noisy quantum era, right? So that's one of the problems that we have right now with respect to quantum computing, because of the extensive amount of thermal noise that a quantum computer has to endure. So results are may not be that accurate, though fast they might not be that accurate, right? So the way to go right now is not fully invest in quantum computing, but to invest in something of a hybrid computing, where you don't forget about the classical optimization, classical computing, but you assist the classical stuff with your quantum stuff. So wherever your computation requires some assistance, means an analogy that you can think of is that you don't, so you have your car, let's say you have your petrol car and you have your diesel car. diesel cars naturally have very high torque, right? They have very high. Do you understand what torque is? Or do you understand the difference between horsepower and torque? A diesel cars usually have very high torque. So that more torque means it will allow it to climb or push the vehicle, albeit at a slower speed, but it will be able to push it. And it doesn't need so that's why you'll see that trucks and all those things, they are they don't have that much of a horsepower, but they have tremendous amount of torque. But racing cars, they don't need that much torque. They have a lot of horsepower in them. So an intermediate thing where that recent cars have developed is something called turbo. Have you heard about turbocharged cars? Okay, so it doesn't have to be that the car is full on horsepower. Okay, so what does a turbo do is that it takes some air and puts it into the engine to burn the fuel for a very small amount of time so that it gets the kick it needs. Okay, so by doing that, it hasn't compromised on the fuel efficiency, but it still has given the car that instantaneous kick that it's needed. So similarly, in hybrid quantum classical computing, we do the same. We do not replace the entire classical base or classical computing with quantum. We just assist it where it's needed, so that means if you have a combinatorial problem somewhere, if you have a highly non-convex problem that you want to search for a solution, okay, you might be you might not find a optimal solution in the classical space, so then you look towards the quantum space. So anyway, so we have the Pauli X, the Pauli Y, Pauli Z gates. Then we have the Hadamard gates. So these are all classical gates. So the identity everyone knows, it doesn't change anything. So it's similar to a classical gate. The Pauli X gate basically flips it. In classical terms, you can call it a NOT gate. Okay. The Hadamard gate is the one that makes the superposition work. Okay, so can anyone tell me in the Hadamard? So we have it divided by a square root of 2. People who don't work on quantum. Anyone? It's a normalization, but why do we do that? Yeah, so we need to normalize it to keep the probability or keep the power equal to 1. So many of you do simulations, right? So you do Rayleigh fading channels. If you remember, when you are generating a Rayleigh fading channel with a RAND or something in MATLAB, so what you do is that you normalize the complex part, the real part, with square root of 2 as well. So basically, you are trying to keep the power constant so that it's equally, both the states can equally be probable. So, yeah. So, unity operations in quantum, they are reversible, and the rotation operation in quantums, they are written like this. So we can all visualize it from this block pair. So, for example, if it's a Pauli X, let's say it's a Pauli X. So what will happen is that if you have an identity, do I have the, yeah. So if an identity matrix will look like this, and the Pauli X will, what it will do is that it will just switch the bits. Okay, so the zeros becomes ones and the ones become zero. That's all. Okay. And similarly, for the case of Pauli Y, so it will just change the phase. Okay, it will just change the phase. And for the Pauli Z, it will change the, no, so for Pauli Y, it's going to change the phase, and it will change the phase as well. And for the Pauli Z, it's going to just change the phase. Okay, and the Hadamard is it's just normalizing it. So this is a notation you will commonly see in quantum circuits, and this notation is basically the notation of measurement. So once a quantum bit passes through this measurement, then you'll get either a 0 or 1. So you have to decide what means the quantum bit is going to collapse and it's going to come to that. So this is an example of how measurement happens. This is an example of how measurement happens. So let's take the example of a Pauli Z. So what does, if you remember, what does a Pauli Z does is that Pauli Z, it basically changes the phase, right? It basically changes the phase. So measurement in the Z basis will give two possible outcomes. So it will either be +1, it will either be -1. And so probability of +1 will be given by the squared magnitude of the alpha, and the probability of -1 will be given by the squared magnitude of beta. So after measurement, this means either of it will collapse to either of 0 or either of 1. Okay. So similarly, this also happens for the Pauli X state and for the Pauli Y state as well. Okay. So in the case of Pauli Y state, it's a bit little complicated since both the phase as well as the bits they change. So now the states they're going to look. It could be either the ket I or ket -I based on the measurement. Okay, so I'll skip a few of those slides. I'll try to. So I have until what time? So right now, what is time? 4:15 or 5:15. I have 4:15.
Excuse me.
Yes.
For the example, I have two states, 0 and 1.
Yes.
How to define the two bits for that case? And I'm not sure how to define the number. For example, we say
So how do you take the number of qubits?
Yeah.
Okay. So basically, it again depends on the amount of information you want to transmit. For example, it's similar to a classical bit only. For example, when you take an analog signal and make it discrete, and then you do the quantization, so you can express the signal in 2 bits also, in 4 bits also. The higher the resolution, the better will be the digital signal that you can again get the analog signal back when you are passing it through a filter, right? A similar analogy. So 4 qubits is going to give you more resolution, 2 qubits is going to give you less resolution. But 4 qubits is going to make the quantum circuit more complicated, and 2 qubits is going to make the quantum circuit a bit less complicated.
So before you find
Just in 2 dimensions. Yeah, it's possible to have multiple dimensions as well, but then you have a very big quantum circuit. So right now, the simulators that we have, like the IBM SKIS kit, so it doesn't allow for more than a few qubits, so that's why, and whatever optimization searches or combinatorial problems that we solve, so most of the problems, I think up to 4 qubits is sufficient to get the results. Yeah, so again, continuing with your question only. So basically, till now, I was just showing single measurement, right? If you do multiple measurements, then you have to take the expectation. So, and again, this expectation property also is like it works similar to classical expectation, where it's the sum of the probability of each outcome. Okay, so for example, for the Pauli Z basis, if you take the expectation of Z, since the rest of them will be measured in zeros and ones, so it's going to be alpha square, square of alpha square minus square of amplitude of beta square. And similar to classical, the variance is nothing but the expectation of, I think I've made a mistake over here. Yeah, I just wrote a mistake. No, it's fine. It's fine. It's correct. It's similar to the classical case of variance as well. So when you have multiple measurements, even with single or two qubits, so what you do is that you take the expectation and variance, and you can apply it to all the gates, be it the Pauli X, Pauli Y, or the Pauli Z. So, and all this Pauli X, Pauli Y, and Pauli Z, if you talk about linear algebra, we have the basis functions. So these are the basis in terms of, it means basis means it's they are the smallest, and you can build up from those, similar to linear algebra concepts that we have. So two classical bits, they have this 4 possible options, but two qubits also have 4 basis states. Okay, but the options are not maybe more, but these are the 4 basis states that this 4 qubits have. And because we have the case of superposition, and when you have this 4 basis states, so you need to add 2 more probability weights to them, so that when you do the normalization, everything becomes equal to 1. And at the end of the day, so what will happen is that the tensor product of single qubits will be, so how do you get this 0-1 state or 0-0 state? You just have to do this tensor products among the other qubits. So I'll just skip this a bit, and this, I think, Professor Octavia spoke about yesterday. So I've shared the slides with you, so I'll skip some, and I had a lot of things, but because of time, we are not going to talk about those. Yeah. Let me talk a little bit about quantum teleportation. Okay. So teleportation is basically a very fundamental protocol in quantum information theory or quantum information processing. Okay. So whatever we spoke till now is quantum computing, but quantum communication is a bit different. Applying those quantum properties of nodes, what we can see is that in a quantum network, there's quantum states that you have. So you can have different quantum nodes, and the link between two nodes can be, we call them as quantum channels. And this quantum states of each nodes, it can be transferred to the other when if they're in superposition. So what happens is that if some of the node is down, then whatever state this node is in, it can be instantaneously transferred to this node. So that way, what happens is that the link never gets broken. Does that make any sense? So in quantum networks, what happens is that in physical communication networks, multiple hops, the link frequently gets broken, right? So if some of the nodes get down, then the link, there's no link between node A and node C, because node B is broken. But what happens in quantum teleportation is that if you find that some of the node is broken because they're in superposition, so the state of this node can be immediately transferred to the state of the other node. So this is how a quantum network works actually. So I was giving the example of Alice and Bob, and so basically what happens is that Bob's qubit is in the state that Alice wanted to transmit. So eavesdropping really becomes almost impractical. Okay, so this is so using this, and this is again the same protocol of this quantum teleportation with that your Alice and Bob shares this entangled pair of qubits. Okay, so basically the idea is that means the Alice, its initial state is that it needs to be teleported is is given by this get psi, and then Alice and Bob they share a build state which is given by, let's say, 5 plus get psi, get psi 5 plus. Then the inner product between these two is given by this. And this again happens through the product of each of the quantum bits. And what happens is that Alice then performs a Bell state measurement. Then that basically determines the state of her qubit. And based on that measurement, or based on the measurement outcome of Alice, then Bob immediately applies a unitary correction. And that could be either poly X or poly Z, or it could be even a combination of X and Z, or even Y, or something like that, right? So in that case, so cloning becomes absolutely difficult because the number of states becomes almost infinite. So this basically again is the fundamental of quantum key distribution, and similar to the entanglements of the nodes. Okay, so here basically what happens is that there's a public quantum channel and there is a classical communication, and both happens together. And how it happens is that the secret keys that you want to share, or we share today using classical communication, that secret key now uses quantum properties. Okay, so until and unless you decode those quantum entanglement, so you are not able to decode the complete information. So what happens in QKD is that this BB84 is the protocol of QKD. What happens here is that the transmission of this quantum states happens in parallel to the normal communication to basically put an extra layer of confidentiality to the communication. Okay. So when you do quantum security, for quantum communication, so this there are 3 phases of ensuring the security. And one is the authentication, that is means computer science people will know that how the handshakes happen and all those things. And then there is the quantum part, which is the key generation part. So Alice will basically prepare a qubit, and then Alice and Bob will exchange classical information to confirm the measurement, the basis of measurement. And the final is the encoding part, where we use classical post-processing as well. Okay, so eavesdropping again becomes, as I said, becomes very difficult, because as soon as Bob and Alice they find discrepancies in their quantum basis, they know that the Eve is basically intercepting, as I said earlier. So I'll skip past a few of those slides. So there are a lot of challenges of quantum communication as well. Okay, so nothing is ever going to be all rosy. So since quantum communication, a lot of it has to do with photons, and photons are something. There's a this photonic loss is a property that basically complicates quantum communication a lot. Okay, so when it comes to long distances, these photons cannot be relied upon, and you're going to lose information. So what you need is that in quantum communication or quantum information theory, what we need is that we need something called quantum repeaters. They're quite similar to classical relays, but again, different in the sense that now what you're trying to deal with is entanglement and superposition. So this photons, basically, when it transmits from one node to the other, so in quantum networks, they will use something known as the entanglement swapping. Okay. And as we saw it in the quantum networks case, nodes, they are basically entangled. Okay. So when you have multiple entangled nodes, then you can actually reach over distant, you can reach far, and so practical quantum networks will require more amount of routing, will require plenty of routing, and also will require plenty of multiplexing. Okay, so let me now look at a practical example and some of the works that we did. So I think Professor Octavia already went through this. So I'm not going to go through the Shor's and the Grover's algorithm today due to lack of time. I'll straight away move to some practical examples. Yeah. So one of the examples that I would like to discuss in the last 15 minutes that I have is about ORAN or Open RAN. I'll just drink some water and then continue. If you have some questions, you can ask me now. Yes, please.
So basically, we know that we cannot transmit signal faster than speed of light. Right?
Yes.
And here we use the term quantum entanglement. But here, in general, here we are using for encryption or some kind of
Okay.
to provide security. So
Okay.
why we use the term quantum communication?
Okay.
Like if it's not using in the communication part.
Okay. So first of all, I think your question can be divided into two parts, actually. So one is that you said that we can't travel with the speed of light, right? Yeah, that's a very good point. So quantum communication is not about transmitting information through the speed of light. It's not that. So there's a particular misconception that if you use quantum, that means you're using photons, and so we are using we are going to travel with the speed of light, but it's not that. It's basically how two particles. So a quantum physicist will look at quantum through optics. Okay, it doesn't necessarily have to be photons. Quantum doesn't necessarily have to be photons. It is matter. Matter, as we see, it could be any matter, but at an atomic level. In the atomic level, everything behaves the same. So if I break you down in the atomic level, or if I break this table down in the atomic level, we'll see that we are the same. Have you thought about it? If you break this down at an atomic level, and if I break you down, so it's made of carbon, you are made of carbon as well. So it's just that the atoms combine within us or with this table in such a way that we are alive, and it's not. So similarly, it's not about just optics. Okay, it's about any kind of atoms at that atomic level, how it behaves when interacting with another atom. That's the idea that Einstein had when developing quantum. Okay, so that was the first part of your first answer to your first part. And regarding what is the communication part here, I had told you about, yeah, before we move into this example, I think it's a good time to answer that, is that about teleportation, or I spoke about teleportation, right? So in terms of sci-fi, forget about real and all those things. In terms of sci-fi, what I want to say is that, for example, what is that called? you were thinking something and someone else is, what is it called, that English term? Telepathy. Telepathy. So it's something that if one particle is located in Kaohsiung and the other one is in New Delhi, let's say, both are entangled in terms of sci-fi, if you want to say. So you rotate you apply a gate to it. You rotate the particle in the X or in the Y or in the Z block sphere. So what happens is that, and then you measure it, for example. The measurement, for example, gives you is a close to 0 or close to 1 state, let's say. As soon as you measure it over here, that particle that is entangled over there, that information is going to be passed to that particle, even though that is thousands of kilometers apart. Okay, so in a way, you are actually transmitting information through teleportation. Does that make any sense? That is not the real. That's a good question. That is not a real. So what is real then? What is real? So the real part is that the quantum networks that we saw, So there are nodes, right? There's a node here. There's a node, let's say 10 kilometers from here. There's a node, another 10 kilometers from there. So right now, what we're using, let's say, optical fiber. Right now, they're using optical fiber. So if we are using quantum, then what can happen is that we can have an entanglement between this node and the node there. Okay, I'm not talking about the node in New Delhi. I'm talking about the node here, and let's say 10 kilometers, 20 kilometers from here. There's an entanglement between these two nodes. So some information from here to that node can now be transmitted at a very lightning speeds by just changing by just applying some quantum gates or quantum circuit. Quantum, yeah, but that's what it is. So as soon as you measure it, there's no more randomness. As soon as the measurement happens, the randomness goes away.
So how can we be sure like this?
Yes. So again, so when you are implementing this circuit in a quantum computer, let's say, so you can't ensure right now that it's accurate because of the noise. If there is no noise in the ideal world, since it's entangled, it's always going to be like that. But right now in the quantum computers, they are limited due to thermal noise. So what is going to happen is that it's not going to be accurate. So that's why I showed you that you need to measure it multiple times, get the expectation out of it. You need to measure it multiple times to get an accurate result. Okay? Make sense?
So we can just say that this application is more related to like, security or computation.
Security, computation, as well as transmission of bits as well. Transmission of bits as well. So you change something over here, the change reflects in the next node. And more than transmission of bits, is more about networks. Why networks means that, as I said, so if the link between A and C, there's a B node, and the B node is not working right now, then the entanglement can be passed on to C. And without the B node, A and C can be entangled, albeit but with certain noise, but A and C can be entangled. For the case of classical communication, what happens is that if B is not working, then entire network goes into outage. If we have a relay kind of setup, the entire network goes into outage. But here, it doesn't go into outage anymore. So in terms of networks, then it works. Okay. So ORAN, so Open Radio Access Network. So this is a concept that has evolved from the days of cell-free MIMO, cell-free message MIMO. Okay, so basically, currently in the cellular structure, what we have is that we have base stations. We have base stations. Each base station has its individual cell, and what happens? How we users connect to base stations is that we move from one base station to the other. There is a handover that happens between one base station to the other. I think many of you would know how mobile communication works. Is that you have to when you enter a network, your mobile phone automatically does a handshake with the base station, and there are certain slots that it can offer. If the slot is empty, it's going to accept you. So sometimes you see that when you move from one place to the other in a train or a bus, what happens is that you're talking on the phone and suddenly the call drops. Okay, and sometimes it doesn't drop. So basically what happens is that you're moving from one cell to the other cell, and your base station hands you over to the next base station. But if the next base station is not, if it's all the allocation, if it doesn't have any slots for you to allocate, then it's not going to be able to accommodate you, and then the call is going to get dropped, right? So right now the cellular structure is kind of limiting. So everything was centralized, the processing, everything was to happen on the base station itself. Okay, the new radios and all those things in 5G, all the processing is to happen on the base station itself. So now what the next generation of cell-free architecture looks like is that is going to be distributed instead of centralized. So there's a core network, and there is the radio unit. Then there is the baseband unit that is going to manage the radio resources. All right, and and the core network, what it does is that it just manages the access, manages the mobility and inter-network connectivity. Okay, and so this ORAN, I'm not going to go into all the nitty-gritties of ORAN, but what I want to tell you is that. Where is that? Yeah. So if you look at this slide, what happens in ORAN is that there's a lot of processing that this RAN intelligent controller has to do. Okay. This is known as the near RT RIC. What is the near RT RIC? Is the near real-time radio intelligent controller. All the optimization that happens, for example, in this problem that we have, was the, yeah. If you look at this problem, so this problem that we solved, it's a problem from one of our papers, and so we were trying to minimize the total power consumption of the entire cell-free network, subject to certain parameters which are dependent on the radio units, the activation functions of the GPP, and the number of users, the power constant of the users, and so on. So, and we are trying to basically minimize the power consumption, and that was the optimization problem. And who decides that? Basically, this cloud, it has this near real-time RIC. It has to do all the computation in order to switch these users between these cell-free base stations, right? So this work was basically, yeah, we did a few works, and this work number 1 and work number 2, this basically tackle this problem. And this is if you look at this optimization problem, it's a huge combinatorial problem with a lot of optimization variables, right? It has a lot of optimization variables, and if you try to solve this in the classical way, so you either end up with a very high combinatorial search area, or you end up with a solution which is very, very suboptimal in nature, right? So what you can do is that you can utilize, I'm not going to take 2-3 minutes more. I'll finish soon, maybe 5 minutes. So what happens is that if you use, so one way to solve this kind of problem is machine learning, right? A lot of you have already been using deep reinforcement learning and even LLMs and all those things. You simply train this network and go on. But machine learning, again, has a lot of overhead involved in it, because whatever you do, you need to do the channel estimation over and over again, because there's some coherence time involved with wireless channels. So another way is that we can combine the quantum with machine learning, and by utilizing variational quantum circuits. So quantum annealing is a very nice area for research right now, where you use this VQCs, and you combine them, you combine this quantum optimization. Here we have used this QAA, quantum approximate optimization. And we have used this with classical optimization and used the Cobbler solver. And by doing that, what we are doing is that we are encoding the optimization problem within a few cost Hamiltonian. And this then implements this quantum measurements then are passed through a classical computer, where basically the computation happens in the quantum circuit, and the updating the parameter happens in the classical processor. So by doing that, what happens is that we are using the classical computer just to update the parameters. Okay, so we are actually moving from, in terms of computation, we are moving from order of n to order of log n by doing this. Okay, so I'm quickly going to show you some of the results that we obtained. So this is the convergence curve that you can see here, and basically this, in terms of convergence, you can see that by using the hybrid QAOA, we can reach faster convergence, and even in terms of total power consumption, what you can see is that the hybrid QAA is not consuming that much of a power per user equipment, both for cell-free as well as small cell deployments. And this is some of the results where we have my students, they have compared several end-to-end and local coordination, some radio only, some wherever. These are the different architectures of ORAN. Okay, so either way, what we want to show you is that by using quantum, you can actually save energy, as unlike thought in the industry right now. Okay, but the most important thing that happens is that you end up with very fast convergence compared to some classical mixed integer linear programming methods. Okay, so this is some of the foundational work, and we are still working towards implementing more problems into it. And so yeah, so a few of the takeaways from today's talk that you can take home is that some of the key applications is that you can apply quantum is optimization, then security, as I've said, for the case of QKD, and AI and machine learning with all those VQCs. Then of course, error correction is also one of the future directions that you can look into. So naturally, quantum is going to meet communication, be it through quantum computing assisted signal processing or optimization of wireless networks. Quantum information is something that I couldn't talk much, but it's again a very hot topic, but also a very, very difficult topic. It's information theory in general is difficult, but quantum information theory is on another level. Basically, you take Shannon theory and extend it to quantum channels and hybrid networks and see what bounds you get. You're basically investigating all the entangled communication links and communication gains. Okay, so this is our research group. If you want to, we do just doing some marketing. We do research on RIS and we do research on near field communication. We have recently started working on pinching antennas as well. We are working on quantum, and so we're also doing some hardware prototyping right now through FPGAs, and yeah, you can scan it if you want to know more. So I think, yeah, so that's all from me. This is some of the recent papers on quantum that you can refer to. Thank you.
We can take one or two questions from audience.
Yeah. So basically, the results that we are working on right now, we are not. If you consider, so we are at a very nascent state. Nascent state. We are at a very early state, right, of quantum computing. If you try and think about the power, the cost that goes on to cool the quantum computer, then no. So we are not considering the power required for cooling the quantum computer. Okay, that's different. So we assume that in 10 years and 15 years time, that is going to be as less as possible. So leaving that aside, means in our results also, in our simulations also, we leave that aside. If you see, it's actually more power efficient. Okay, if you leave the cooling part, because most of the cost that IBM takes from this subscription from its users is to cool those quantum computers. Okay. Anyone else to ask anything online?
No question.
Okay.
Yeah, thank you, Dr. Biswas. We have a small token for you.
Sorry, I have a question.
Yeah.
Sorry.
Okay. Please
Thank
go
you
ahead.
so much. Thank you so much, Professor Sudip, for your wonderful presentation. I would like to ask one question, that where is the kind of application, like you did talk a lot about ORAN, so what is the application in the failure? Like I work in the signal processing for comms area. So may you please kind of elucidate or throw light on?
Okay, so basically, yeah, means the ORAN as in means ORAN is a real world example, but what I wanted to say with respect to ORAN is that the signal processing that goes behind computation. So the optimization problem that I showed is basically a power minimization problem. And so that's a signal processing problem actually. So similar to this, we could also have any kind of beamforming problem. That is a signal processing problem where we're trying to minimize the MSC or minimize or maximize the rate or stuffs like that, right? That's a signal processing problem. Again, what you're doing there is that you are trying to, in a sphere, you're trying to find solutions, right, out of many combinations. So it's a combinatorial problem. It's a combinatorial problem. So any kind of combinatorial problem, when you represent it through quantum, so you're going to get faster computation. So any kind of signal processing algorithm, you can have quantum in it. So just in a hybrid way, so you don't actually completely replace the signal processing algorithm that you designed. You basically, what you do is that, for example, if you're trying to solve an optimization problem, you have a cost function and then you have some constraints and then you have the variables. So how you solve is that, for example, you want to solve an iterative problem. So at every iteration, what you're doing is that you're trying to update the variables, right? So the updating you can do it in a classical computer, but the searching of the optimal for that iteration, you can do it in a quantum computer by just implementing a simple 2-bit or 4-bit quantum circuit. So that's going to fasten the computation quite a bit.
Thank you so much, Professor Biswas. It was nice to hear.
Thank you. Thank you.
Thank you so much.